Hi, I'm Jericho McLeod. I'm a senior data scientist here at Elder Research. And I'm going to use some machine learning today to help me identify wines that I should pick up. Now, my goal is to have a wine tasting and compare some specific characteristics of wine to see what I like more. In other words, using data driven analytics to select wines. So I've got malic acid from the UCI machine learning repository dataset on wine, malic acid being what gives wines their sour taste. And I've got information on flavonoids. Flavonoids give wine a general mouthfeel and flavor, but too much might not be a good thing. I'm going to use a method to identify anomalies in these two characteristics. It was originally pioneered by Liu, Ping, and Zhou. That method is isolation forest. You might have heard of other machine learning methods using the word forest, and there's some similarities. The most common being random forest, which use decision trees under the hood, which is a way to separate data out into like categories. In other words, in each group, you get a similar group of things that you then throw a label on and say, these are all one thing. Unlike that, an isolation forest seeks to separate data completely. It does that using a thing called a binary tree. Just as a quick example, if I had two data points right here, and I separated at 5 on malic acid, these two are separated. Now, if I want to actually apply this to real data, what I'd be looking for is how easy it is to separate a data point from the rest of the data. So if I look at D, anywhere between 5 and 6 will separate D in one cut. E, similarly, at 4.5 is completely separated. And that entire range, if we were randomly drawing these cuts, I have a pretty good probability of hitting that compared to hitting something over here that separates out a single point. Now, another example is A in the middle here. It takes a minimum of 2 cuts. And then similarly for C, I have to make 3 cuts to completely separate it from all the data. And then B over here, it takes 4. I have to completely box it in to separate it. So if we actually write these out, I have A, B, C, D, and E. A takes 2. B takes 4. C takes 3. D only takes 1. And E only takes 1. But these are lower bounds for this method. In other words, there's not a way to completely isolate any of these points that's less than that amount. So if we do a lot of random binary trees where we completely separate each point by randomly cutting the data, the least amount of cuts to separate these will move the average for the point. So if we actually apply the algorithm on a computer, we get things like D is a negative 0.05, as is E. But then B gets a positive 0.31, A gets a 0.10, and C gets about a 0.2. Now, when we score these, I'm using the scoring method that's common in libraries like scikit-learn. So anything negative is going to be an outlier, and anything positive is an inlier. And you can even tell this being more central to the data, it gets a higher number. And as you get lower, it's becoming more like an outlier. And then D and E are clearly outliers in my data. So those are the wines that I would pick if I wanted to compare malic acid and flavonoids directly. And then I could use something like B as kind of a control, middle of the pack. Now, there's a few advantages to using isolation for it, and not just on this data set. Namely, it's very fast as a method. 2, it generalizes quite well. By drawing a lot of random trees over and over again, it doesn't fit very precisely to this data, which means I can apply it to new data that I haven't seen before. And 3, it doesn't take a lot of memory. That makes it really good for large data sets if you're concerned about that being an issue. So that is, in a nutshell, how I can use isolation forest to help select a couple of wines for a tasting this weekend. Thank you.